Welcome to the afternoon session. I'm going to talk about our work that I've done with my colleagues in Facebook AI research. In this work, we developed a unified network architecture to solve both instance and semantic segmentation simultaneously. We call this approach panoptic feature pyramid networks. In the last decade, researchers were mainly focused on two different image segmentation tasks. First one, semantic segmentation. The goal is to assign a semantic label to each pixel on the image. The second task is instance segmentation task. This goal is to delineate the objects of things classes with their masks. Predicted masks can be used for future analysis then. Recently, the task that combines both semantic and instance segmentation has gained a lot of attention from our community. Here, the goal is to assign semantic label to each pixel of the image and split different instances of the same semantic class into different segments. The unified task requires methods to predict richer semantic scene information in a coherent way. The task has a new quality metric that treats classes with and without separate instances in the unified way. A lot of modern segmentation datasets have ground truth annotation for the task and run panoptic segmentation challenges and leaderboards. You can find more information about the task at the poster session tomorrow with some familiar names on it. Given how well-studied semantic and instance segmentation tasks are, the most straightforward way to produce panoptic segmentation is to combine two independent networks. First, use the best-known architecture to predict semantic segmentation. Then, use another architecture that is proven to be good for instance segmentation. Finally, to obtain panoptic segmentation, we can combine the outputs of the networks together. While this approach is straightforward, the need to run two different networks makes the method very inefficient in terms of compute and memory usage. Moreover, this two networks approach makes it harder to build an end-to-end system on top of it. In our work, we propose a unified network architecture that produces semantic and instance segmentation simultaneously. Our architecture starts with a single backbone for both tasks. We employ feature pyramid network, or shortly FPN. The backbone produces a set of feature maps with different spatial resolutions. We use FPN output feature maps to build instance and semantic segmentation heads. First, we use mask-RCNN head to produce instance segmentation. This architecture has proven to be a very strong approach for the task. We call this head region-based recognition head. For semantic segmentation, we use very simple pixel-wise recognition head that uses the same FPN feature maps as mask-RCNN head. In this head, we first process feature maps at each scale independently, bringing them to the same spatial resolution. Then, we sum up the feature maps and predict the final scores for semantic segmentation. We call this head pixel-level recognition head. Semantic FPN does not use dilation to preserve spatial resolution throughout the backbone. This makes the architecture more computationally and memory efficient than many existing semantic segmentation frameworks. Surprisingly, this simple pixel-level recognition head on top of the FPN backbone achieves competitive performance for the task. We won Coco's Tough Challenge using the early version of the architecture. And in our work, we also demonstrate that the architecture yields performance on par with well-known Deep Web version 3 and version 3 plus methods. Finally, we consider the whole unified architecture with single backbone and two heads that produces semantic and instance segmentation simultaneously. In our experimental evaluation, we use two segmentation datasets, COCO and Cityscapes. Given the same overall computational budget, we compare panoptic FPN with two independent systems for semantic and instance segmentation. In this setting, panoptic FPN outperforms mask-RCNN for instance segmentation. Its performance is superior to semantic FPN in terms of mean intersection of a union as well. Finally, panoptic quality of our approach exceeds the performance of the combination of two separate networks. On this slide, we show some qualitative results for panoptic FPN. In conclusion, panoptic FPN is a new, simple, and very efficient approach for panoptic segmentation. In the future, we expect all new panoptic methods to use it as a strong baseline. That's all from my side. Please come talk to us at our poster later today. Thank you.
Hello, everyone. I'm Xinggang Wang from Huazhong University of Science and Technology. So this is my work, our work joined with horizontal robotics. Title is mask scoring RCN. We work on the problem of instance segmentation. Our method is based on mask RCN. It extends fast RCN by adding branch for predicting object mask. It uses classification score as instance segmentation score, termed as mask score. However, it is not suitable to use classification score as mask score directly. The mask quality LU between the predicted mask and its ground truth mask, termed as mask LU, is usually not well correlated with mask score. Here shows the example. This kind of situation happens in many situations. So in this example, it shows the result. The mask LU is 0.69, while the mask score is 1. Obviously, this is not suitable to use classification as mask score in instance segmentation. Therefore, our motivation is learning a calibrated score according to mask LU as shown in the following figure. Mask LU and mask score are not well correlated in mask RCN. So our mask scoring RCN want to solve this problem. We decompose this problem into two tasks. One is the mask classification, another is LU regression. For mask classification, it directly uses the classification score from the RCN stage. For LU regression, the LU can be learned by our proposed mask LU head. So our level is very simple. We extend mask RCN by adding a branch termed as mask LU head for predicting mask LU. The following figure shows the network of mask RCN, and our mask scoring RCN adds another branch. So the input is the concatenation of ROI line feature and the predicted mask. After that, we use the predicted mask to refine the mask score. The mask LU head is simple. It contains several convolutional layers and fully collected layers. For mask score refinement, we use the predicted mask LU multiplied with classification score to get the new score as the final score. We show our results in different backbone networks. The results of ResNet 18, ResNet 50, ResNet 11. As shown in the paper, we obtained about 1.5 MAP improvement, especially at AP at 0.75. We have more than 2 MAP improvement. That shows we can get improvement in different backbones, including large network and small networks. Next, we show the results in different frameworks: fast RCN, FPN, and the last one, DSN plus FPN. As shown in the paper, we still get improvement in different frameworks. Next, we show the results in COCO test DV. The results fast RCN, FPN, and DSN plus FPN. Compared with the step results, we get good results. Here we have some discussions about the design choice of mask LU head. The results show the performance is stable to different designs. Finally, we made some discussion about the running time. We compared to mask RCN, the testing time is basically the same, whether using ResNet 18 or ResNet 11. For the quality of the predicted mask LU as shown in the figure, there is a good correlation between the predicted mask LU and the ground truth mask LU. For ResNet 11 and ResNet 18, the correlation coefficient are both 0.754. It indicates that our predicted mask LU is of high quality and insensitive to different backbones. Okay, the next slide shows our code. And thanks for your attention.
Hello, I'm Huang, and this is a joint work between Huawei NOHA's ARX Lab and Sun Yat-sen University. And I'm happy to present our work, Reasoning-RCNN, Unifying Adaptive Global Reasoning into Large-Scale Object Detections. So what is large-scale object detection? This means to localize and recognize thousands of categories objects in one image. This results more severe long-tail problem and more teeny size problem and heavy occlusion and class ambiguity than normal detection. However, the most current detection method lack reasoning. They usually treat proposals separately. They depend on high-quality feature representation and sufficient label data. But that is not the case for large-scale detection problem, and so such methods are failed. Recently, how to install visual reasoning into network brings to people's attention. Earliest work focused on post-processing to align semantic correlation between objects not in an end-to-end style. Some work try to model spatial relationship in an implicit and uncontrollable way. Recent work consider a graph structure to incorporate knowledge, but they build a fixed graph and share feature among proposals. So we want to develop an in-place and simple global reasoning network, which can be adaptively propagate high-level information among categories within explicit ways. For example, human can identify the teeny size object CCTV in the red bounding box because of global knowledge reasoning. Human will first search his memory for the object similar with appearance category that inspire us to design the global semantic pool module in our model. And furthermore, rich common sense knowledge can also help to make a correct recognition. This small electrical mental object, which is installed on the building and is watching car, so it is more likely to be a CCTV. Based on those motivations, we proposed our Reasoning-RCNN, and this is our mainly our frameworks. So our Reasoning-RCNN can be stacked on any existing two-stage detection networks. Specifically, we will collect the weights of classifier from the base detector to create a global semantic pool M. This is analogous to the memory in human brains. And then a category-to-category undirected knowledge graph G is defined, such as relation, attribute knowledge, and sharing during training and testing. To avoid the noisy information, we further compute an adaptive attention from base features, which can help us to emphasize more important category and suppress useless one. Finally, representation in M is involved by a GCN according to adaptive global graph reasoning, and then we use soft mapping to transfer categories information to region proposals. And we use enhanced proposal feature to get a better detection result. This result shows that our baseline model, fast RCN, tends to ignore real categories and ambiguity objects, while our Reasoning-RCNN can detect them. We also evaluate our approach on large-scale detection dataset VG with 1,000, 10,000, and 3,000 categories, and ADE with 400 categories. This table shows our approach with relation knowledge outperform the baseline method on all datasets. And to compare with more existing methods, we also implement our approach on Pascal VOC and COCO. Our Reasoning-RCNN can improve from 37 for FPN to the 40 for about 43 MAP with our method, and with 2 million more parameters and 3 ms inference time. We also plot the clustering of the enhanced feature. It can be found that the enhanced feature can show our method can learn the relation knowledge, and detailed analysis can be found in our paper. And thank you, and we plan to release the code and train model in this month, so thank you.
So we have time for questions. There are 2 mics towards the front of the room on both sides, and 1 mic runner in the balcony. Okay, so maybe I can start. So I have a question for the author of the mass scoring RCNN. So can you comment on which categories you see the most boost and why?
Sorry?
Can you please comment on which categories you see the most boost and why?
Okay. Actually, I don't know which category gets most improvement, but the problem is that the problem happens when there are occlusion and the shape of the object is very strange. In this case, the mask is not so good. It may focus on the discriminative part of the object. That the score could be very high, but the LU is very bad. That we need to use this kind of strategy to calibrate the score.
Is there a question up in the balcony? It's hard to see. Okay, so if there are no more questions, we can move on to the next speaker. So could you please come up?
Good afternoon, everybody. My name is Nils Murrugarra, and I will present our work on cross-modality personalization for retrieval. This is a joint work with Professor Adriana Kovashka from University of Pittsburgh. Consider the following application. You have taken many pictures at a recent vacation, and you want to create a blog post automatically, which include captions for each of the pictures. A friend suggests that you use automatic image captioning tools. You try them, but you find that the annotations you retrieve are rather generic. They don't capture your personal experience and emotions. Thus, we observe that existing methods annotate images only based on the pixels, but fail to capture context specific for individual users. We seek to enable personalized captioning by modeling how the perception of different users varies across modalities, including gaze, writing style, and personality. Our key idea is that perception is affected by our experience, bias, and personality. This perception can be captured how we look at the images and how we describe them. We examine the relationship between gaze, personality, and image captioning by learning them together. For example, in this advertisement, 2 annotators focus on the children, and they write, I should buy this car because it's good for my family or because it is safe for my children. In contrast, a third viewer focuses on the style of the car, and her annotation is, I should buy this car because it's elegant. We hypothesize these differences in annotations correlate with personality and experiences. We first collect caption and gaze data along with responses to personality surveys for images in 2 datasets, our ads dataset and COCO. These annotations are available on our website. To collect the data, we develop an interface with 3 components. The first component is the gaze capture component, which presents viewers with a blurry images, and participants should click on it to reveal parts. Then we ask for a text annotation, and finally, we ask for personality survey for each of the annotators. We first collect gaze data along with response for images into the. Next, we represent gaze with using the last convolutional output for an inception before CNN masked with our gaze map. Text is represented with a globe embedding, and for personality, we use a 10-dimensional feature vector. We find an embedding space where paired samples are close by, and we consider 3 types of paired samples. Describe it next. We use triplet learning to learn an embedding space. Our base network ensures that paired samples provided by the same user on the same image should be similar, and unpaired ones should be dissimilar. We also add two more types of constraints. We call the first one content constraint, where data provided on the same image are similar, and data on different images are dissimilar. Finally, we add style constraints. Data from the same user should be similar, and data from other users should be dissimilar. Our method is the combination of the three learned embedding described so far. We evaluate our method using three task-specific networks. The first learns to map gaze to text, and vice versa. The second maps text to personality, and the third gaze to personality. We consider two data split strategies, and for both data splits and both data sets, our method outperformed the baselines. Our method especially helps for text to gaze and gaze to text tasks. Then we train a joint network where the constraints for all three modalities are embedded in the same space. We compare our task-specific network with this joint setup, and we observe that joint learning is beneficial. We also show one qualitative result. Please come by our poster for more. Here we see that the annotator marked in blue mentions appropriate companionship, which is related to this user's family-oriented personality trait. In contrast, the orange annotator mentions, make me a sexier person, which is consistent with this self-centered personality trait. Thank you for your attention, and see you at poster 1476.
Hi everyone, this is Nam. I'm here to present our work composing text and image for image retrieval. This is done in collaboration with folks at Google while we're there. So in this paper, we studied the contents-based image retrieval problem. The two common applications is that where the query can be text or image. In this work, we studied a setup where the query is an image text composition. So the use case is that a user wants to search for images that's similar to a reference image, but he or she can also add a text to specify some kind of change or modification. And the motivation is that this composition is more expressive than like image alone or text alone. So these are the three data sets that we experimented with. First, we used a clever toolkit to create a synthesized data set where the images are just like very simple scene of objects with different shapes and colors. And the modification here is just like add, remove, or changing the object colors. We also use two existing object attribute kind of data sets where the modification is changing the attribute value. So it's basically attribute feedback retrieval, but we retain the attribute to be text. So this is some example query. Given query, you can see what the target, correct target image should be retrieved. And given these labels, we can train an image retrieval system. I'm speaking too fast or something. Okay, let's move on then. So we just employ standard deep metric learning technique to learn an image retrieval system. So basically, we just learn a CNN to encode the images so that the query and the correct targets is closed in the image feature space. So we just employ very standard kind of loss function like triplet loss for that purpose. And it's kind of very straightforward and easy to train such system. The only difference that we would make here is that because our query now is an image plus a text, so we have to change the encoder of the query to take that and output a feature. But the rest of the pipeline will stay the same, the loss function will stay the same. So in this work, we mostly focused on studying what to fix in that yellow box. We studied very simple space like, for example, feature fusion. We can do encode the image and the text separately and then concatenate them or something like that, which has been done in a lot of previous papers. Another baseline is what you can leverage existing architectures in, for example, captioning or VQA area, because the architecture can also take an image and a text and output something. So they fit in our use case, we just exactly plug the architecture in and it should work. Additionally, we also try out our slightly different composition model with also very Skype symbol, which just encode the image and encode the text. And then we can just take the reference image feature and then perform gating and add a residual value from the text feature. So the motivation is basically instead of creating a brand new feature in a new feature space, we are just pretend that we are in the same image feature space and we're taking a walk from the reference position to the new position. So basically, this just imposes a strong prior on what the output feature vector would be, so it's quite simple. These are some example retrieval results. On the left, we have the query with image and text, and on the right are some top-ranked image returned by the system. As you can see, we do retrieve correct images sometimes. This is the quantitative result on the three data sets, where we compare performance with different kind of baseline and also our own methods. You can see that in order to effectively perform retrieval correct, you have to actually compose both the image part of the query and the text part of the query. Okay, to summarize, so in this paper, we will study the image retrieval problem where the text query is more expressive. It can image plus a text, and we benchmark different existing baseline and other methods in the VQA architectures, and also we propose slightly different composition methods. Thank you for listening.
Good afternoon, everyone. My name is Xiaobin Wang. I'm from Samsung Research, China, Beijing. My paper is arbitrary shape syntax detection with adaptive text region representation. At the beginning of my presentation, I will give out the motivation. In syntax detection, most existing methods use polygons of fixed number of points to represent text regions of different shapes. But we think that this is not suitable, such as in CTW 1500 dataset, 14 points is used. But it is too many for most text regions, while they are not enough for very long and curved text regions. Such as the figure, 6 points may be enough for this text region. Then the idea comes out that we consider using polygons of different numbers to represent different text regions. It is a key idea of this paper. We have used 2 ways to represent text regions. First, we consider use corner points. One corner point is predicted each time step with RN, but we find that it's not easy to learn because prediction direction changes as shown in the figure. Then we consider using pairwise boundary points. 2 pairwise points on top and down boundaries of text regions are predicted each time step with RN. It fits the symmetry of text regions and works very well. So the second one is chosen in the paper. Here are some examples of text regions with adaptive representation. As shown in the figures, for straight line text regions, 4 points may be enough, while for some curved text regions, 6 points or 12 points may be needed. Based on the proposed idea, an arbitrary shape syntax detection method is proposed. The method is also based on faster RCNN, but a new branch is added for adaptive text region representation learning. The red box is the added new branch for text region refinement. In the new branch, LSTM is used for text region representation learning. At each time step, the input is the outputting feature of this text proposal, and the outputs are two pairwise boundary points. Prediction continues until a stop label is predicted. Then we will get text region polygons as the detection results of our method. Finally, we give out the experimental results on two benchmarks, CTW 1500 and the total text dataset. The proposed method achieves state-of-the-art performances on both of them. That shows that our idea works very well for text regions of different shapes. And some samples of our experimental results are given out. The proposed method can process text regions of different shapes, but it fails in some very difficult situations, such as dot text regions and text regions with a very large character. We will consider solving the problems in our future work. That's all. Thank you very much for your attention.
Okay, so we have time for questions. Okay, then I'll do another. So for the second speaker, I have a question about whether you can comment on some of the failure modes of the retrieval that your system produces.
Failure mode, actually, let me just have to think about it. So I think a lot for example, in the asynchronous data set, the failure mode is I think seeing that very similar, only like the color is slightly different. And on the fashion data set, the label cap noisy, and it's kind of even addressed, even the size of the label and the attribute might not even accurate. So if you look at the images, a human look at the visual result, it cannot say that it's correct or incorrect. That's what I can send nothing up.
Okay, so since there are no more questions, let's thank the speakers again, and could the next speaker come up?
Good afternoon, everyone. I am Liu Songtao from Beihang University, and today I'd like to talk about adaptive NMS refining pedestrian detection in a crowd. And in this work, we focus on a challenging problem in pedestrian detection, crowd occlusion. Crowd occlusion is that people are occluded by each other. As people have very similar appearances, the same features tend to be less discriminative, making it a more challenging problem. And the current solutions for crowd occlusion mainly focus on the robustness of bounding box prediction. They add additional penalties named repulsion loss or HG loss to produce more compact boxes. And in this work, we started the crowd occlusion from another aspect. We know that the CNN-based detectors usually adopt greedy NMS to remove highly overlapped duplicates. But in crowd scenes, it meets a dilemma. A lower NMS threshold leads to missing highly overlapped objects in a crowd, like the blue boxes in the right, while a higher threshold brings more false positives, like the red boxes in the right. And specifically, the greedy NMS and soft NMS first pick a proposer with the highest score at capital M. And then they rescore the bounding boxes around M according to their overlaps. The rescoring strategies may be different, but they hold the same hypothesis that the boxes with higher overlaps with M should have a higher likelihood of being false positives. But this hypothesis is not true in crowd scenes, where people are highly overlapped with each other and should not be treated as false positives. So we propose a new adaptive strategy that we adopt a higher NMS threshold in the crowd region to preserve crowded objects, and we also adopt a lower threshold in the sparse region to remove false positives. We first define a density to describe the degree of crowding for each object. The density of an object is the max bounding box IOU with other objects in the ground truth set. With this definition, in crowd scene regions, objects must have high densities, and we just apply high threshold according to their density, and vice versa. For prediction, since we don't have labels, we can't directly get the density for each object. So we designed a subnet to predict the density, just like predicting locations and classifications. The subnet takes the bounding boxes, the classifications, and the reduced CM features as input, and then predicts the density for each proposal. And this subnet can be added for both two-stage detectors behind the RPN and one-stage detectors. We apply the adaptive NMS on the two-stage detector Cross-RCNN and the one-stage detector IFBNet on city person's dataset. Under the common metric of miss rate, the lower the better, adaptive NMS improves the performance for both two detectors. And we further divide the city person's validation set into 5 groups according to their density. And while we look at the groups with higher densities, we see that the adaptive NMS denoted as the gray bar significantly reduced the miss rate, showing its effectiveness in crowd scenes. For visual result, we use blue boxes to denote missing result and red boxes for false positives. When two people are very close to each other, for example, in the second column, both greedy and soft NMS miss the man in the head, but because he's highly overlapped with the man behind him. But the adaptive NMS can preserve the result. And we also find some failure cases that if boxes are not compact, adaptive NMS also brings more false positives with high threshold in crowd regions. And the complementary solution for these cases is to add repulsion loss or AGG loss to produce more compact boxes. So here are our final result compared to other state-of-the-art on city person's validation set. When we add AGG loss, it further improves the performance of adaptive NMS for both two detectors. And we also report the result on another more crowded data set, crowd human, which has an average of 2.4 people per image with density greater than 0.5. And adaptive NMS consistently achieves better result for both two detectors. And thanks for your attention, and welcome to our poster at 31. Thank you.
Hi, everyone. I will present the paper entitled Pointing Box Aunt Beyond Counting Person in Crowd on behalf of the author who are not able to come to CVPR due to the weather issue. This paper was jointly done by Sun University in China and INRA in France. I'm Huang from the Institute of Computing Technology, Chinese Academy of Science. So this work is about crowd counting, which is a technique to count how many persons are in image or video. State-of-the-art performance can be achieved by a CNN-based method, which can be divided into 2 categories, regression-based and detection-based. The regression-based method cuts the problem as regressing a density map, and the integral over the map gives the person count within that image. Such method requires point preparation, means each person with a dot on his head, from which a ground truth density map is generated by blurring each point with a normalized 2D Gaussian kernel. During training, a pixel-wise Euclidean loss is often used to narrow the difference between the predicted and the ground density map. However, this method cannot provide the precise information of the location and size of each subject, which is rather important for the tasks like crowd tracking or recognition in surveillance. Detection-based method, in contrast, can get detailed location and size information, but the premise is that we should have bounding box supervision, means each person with a tight bounding box on his head. Compared with point supervision, the orientation can be very expensive and sometimes impractical in real application. Our goal in this work is to describe as point in, box out, that is to detect the location and size of human head and count them in crowd with only point supervision. We propose a point supervised deep detection network with 4 key components: pseudo ground truth initialization, online pseudo ground truth updating, locally constrained person regression loss, and curriculum learning. Here we show our method, learn to detect and count person in crowd with point supervision. The pseudo ground truth initialization module gives a cost estimation of the person's head size. Specifically, we first compute the distance from each set to its nearest neighbor head, and then set the initial head size at the nearest neighbor distance. During training, we iteratively update the size of each pseudo ground truth bounding box according to the current detection. At each iteration, we first select positive anchor whose IOU with the current pseudo ground truth exceeds 70% and whose size is smaller than the nearest neighbor distance. The updated pseudo ground truth is from those positive anchors that have the highest detection score. We observe that person head in same horizontal line in an image usually have similar size and gradually become smaller in the remote area in the image. According to this, we statistically compute the mean and standard deviation of head sizes within a local area and design a locally constrained regression loss to penalize the prediction whose size exceeds the 3 sigma error bounds. We also adopt curriculum learning strategy to learn from easy to hard with medium density image first. Here are some examples of our method. Beyond counting person, our method can detect objects in natural senses, irrespective of their category. MFE, MAE, and AP are used to evaluate counting and detection performance of our method. As can be seen from these results, our method is superior to existing counting method, and meanwhile can achieve even better detection results in some cases with only point supervision. This is the end of the presentation. Thank you for your listening. Please come to poster number 32 for more detail.
Good afternoon, my name is Javier, and welcome to this presentation about locating objects without bounding boxes. This is the work I was doing with my colleagues while I was at Purdue University, advised by Professor Delp. This all started when we realized that small and highly overlapping objects are particularly hard to detect with bounding boxes, not only for object detectors, but also for humans when we are ground truthing. So we thought, why do we need them in the first place? For such cases, it seems much more natural to detect them using points. You can see an example with human heads, and it's especially hard for plants that are entangled with one another. So we decided to redefine the object localization task to estimate points locations instead. This means that our target is a set of points, and our estimation is another set of points. We start off by measuring the similarity between these two sets of points using the Hausdorff distance. This metric has some nice mathematical properties, but it has the problem that it's very sensitive to outliers. And you can see an example on the right where the distance between these two sets of points is dominated by the worst case, the distance between y1 and x3. So people use the average Hausdorff distance, which mitigates this by replacing the maxima with averages. So ideally, we would like to use this AHD to both evaluate and train our models. The problem is that CNNs, they don't return X in a differentiable manner, so we cannot use backpropagation right away. What we do is modify the average Hausdorff distance to make it differentiable by using the output of a fully convolutional network as its weights. This way, we get a loss between the output of the network and the true set of locations. Another thing we do is replace the minimum, which is not differentiable, with a smooth approximation controlled by the parameter alpha. You can use this loss function as a plug-in replacement in any fully convolutional network, as long as it returns a probability map of the same size of the input image. In our case, we just use UNet. The only thing you need to do is add a lateral network or anyhow you want to estimate the number of points in the image. In our case, we use a small fully connected layer. Then we feed the probability map and the estimated number of objects into a Gaussian mixture model, and we get the final estimate of the point locations as the centroids of each Gaussian. Here, in the next slide, you can see the output of the network using this new loss function as training goes on, and how it converges towards a single dot on top of each true location. In the paper, you can find the proof that this is actually the minimizer. So we tried this with 3 different data sets where the goal is to locate human heads, the center of the pupil, and plant centers. We compared with faster RCNN, where we construct small bounding boxes around each point, and also with methods that are fine-tuned for a specific task. We evaluated this method with a bunch of metrics, some for localization, some for counting accuracy, and we found that it was especially successful when the objects are small and very close to one another. As a summary, this new loss function that we call weighted Hausdorff distance can locate objects in images as points. The key remarks are that it's a natural adaptation of the Hausdorff distance to any fully convolutional network, and it has no notion of bounding boxes, region proposals, or sliding windows. As future improvements, we want to evaluate this using the latest architectures and also do a more in-depth analysis of the effect of the hyperparameter alpha in the smooth minimum. You can download the paper, code, and pre-trained models from arXiv and GitHub, and you can also stop by my paper, which is number 33. Thank you very much for your attention.
All right, so we have time for questions. If you have any questions, please come towards the front of the room where there are mics, or if you're in the balcony, there's a mic runner.
Just to demonstrate where the microphone is. So I've seen this idea of recognition with, or detection with points, and even annotation with points rather than boxes, kind of more and more. Do you think this is going to catch on, or are there too many kind of trade-offs and problems to overcome before it becomes more mainstream?
Yeah, so I think we're going to see it more and more, especially because it's orders of magnitude cheaper to annotate with points. There are a lot of studies about it. But there are some limitations. It depends on the task. If your task requires bounding boxes, then you just need to collect them. There's also, bounding boxes have the notion of size. So for crowd counting, for example, you don't care much about the size, but if you're detecting big objects, you definitely need to have something. Key points are not enough.
Yeah. Hello? Can you hear me? Okay. Well, For the third paper, would it be possible to utilize already pre-labeled data sets that have bounding boxes, and then I think you will just get the centroid or something? Is that something you tried?
No, we have not tried that, but it's perfectly valid. We actually did the other way around. We found a data set that had center points, and then we constructed bounding boxes around them. In general, those data sets, you need some notion of size, but it's worth trying. Thanks.
I have a question for the last speaker. So how do you justify that, because I saw that your model, the output resolution of your network is like high resolution. How do you justify that the ability to detect small objects is because of your proposed Hausdorff distance, or is it just because of the higher resolution?
We didn't test that, but it's very common to have fully convolutional networks that upscale to the same input size of the image. I don't think there's any problem with that.
Okay, because I don't know, because for example, for fast-RCNN, the output resolution is not that high, so probably, yeah, maybe you can do some blush study on this. Yeah, just curious.
Thank you.
All right, thank you. So we're out of time. Let's thank the speakers again. And could the next speakers please come up?
Hello everyone, so I'm Krishna. So today I'm going to present our work on FineGAN. So this work has been done with my collaborator Utkarsh and Yongchao from UC Davis. Consider this task of identifying which of these birds belong to same fine-grained category. It's easy to tell that A and B should not be grouped together with C or D because of their different shape and background. But how about C and D? Their background, shape, as well as rough textures are similar. But if we look closely, we find C and D differs in beak's color and tail's texture. So all four birds belong to different fine-grained categories. All right, what did we learn here? We observed that birds can differ in terms of multiple factor of variation. For example, in this case, they are shape and background. But also there is a natural hierarchy associated with the factor of variation. Some birds can have same background and shape, but they can differ in terms of color and texture. So in this work, our objective is to develop a generative model which makes use of implicit hierarchy to model fine-grained object categories by disentangling different factors of variation associated with them. Prior work on unsupervised generative adversarial network can be largely divided into two types. First type takes a noise vector to generate image in one-shot manner. In second time, images are generated in stage-wise manner, where initial stage generates the background, and later stage stages foreground on top of that. Our idea and motivation differ in that we are trying to model a natural hierarchy present in fine-grained images by disentangling different factors of variation, which turn out to be background, shape, and texture. In the process, different latent variables gain explicit control over discovered factor of variation at different stages in our model. This is overall fine-grained architecture consisting of 3 stages, all of which are trained in end-to-end manner to generate fine-grained images without any mask or fine-grained level. The initial background stage, conditional background code, and a noise vector generate a background image. The parent stage then takes a parent code and noise vector and generate a parent image capturing the object shape and a mask which is used to stitch the parent image onto the existing background. Finally, at the child stage, FineGAN takes the child code and generates an image containing the texture detail and new mask to stitch it on the existing parent image. We now explain why shape could emerge as factor of variation at parent stage. On the left, we see an implicit hierarchy in these real images where the birds have common shape but differ in texture. On the right, we see how FineGAN can generate images hierarchically where multiple children having different texture can originate from same parent image describing their common shape. To facilitate this, we make certain design choices. A group of child codes share a parent code because different categories having different texture can have similar shape. This also means that dimensionality of the parent code is less than that of the child code.
All right, we now show our stage-wise image generation results. Initially, our model can generate background containing no foreground details. Following this, parent image is generated describing only the object's shape. Finally, child image is generated, which fills in the object's color and texture details. These are the results for dogs and for cars. This result shows hierarchical grouping and disentanglement learned by Xinggang. For each parent block, all the generated images share the same parent code reflected in similar shapes of the birds. Each row corresponds to a different child code, which results in different color and texture details. We show similar results for dogs and for cars. This result more clearly illustrates the disentanglement learned between shape and texture features. Across the rows, the child code remains the same, resulting in differently shaped birds having same texture. Along the columns, parent code remains the same, resulting in birds having different texture but same shape. This video best demonstrates the overall disentanglement learned through Xinggang. Here, we're only changing the background code, which changes the background, while both the appearance and shape details of the birds remains constant. I want to emphasize that our work is unsupervised in the sense that we do not use any fine-grained labels or segmentation masks. Now, we're changing the parent code, which only changes the shape of the bird. We now change the child code, which only changes the color and texture details of the bird. Finally, we change the noise vector, which only changes the pose and viewpoint of the bird. As an application, we use Xinggang's learned representations to tackle the novel task of fine-grained image clustering and achieve significant improvements over previous state-of-the-art deep clustering methods. Thank you for your time. For more details, please visit us during the poster session.
Hello, everyone. Today, we will introduce mutual learning of complementary networks for semi-supervised classification. This work was done jointly by South China University of Technology and City University of Hong Kong. In our setting, there are a limited number of label samples and a large number of enabled samples. The purpose of semi-supervised learning is to exploit readily available enabled data to facilitate learning on the limited label data. A widely used assumption of semi-supervised classification is that neighboring data points more likely belong to the same category. Based on this assumption, various consistency-based regularization strategies are incorporated into semi-supervised learning models. And the main idea behind this work is the complementary correction among the component networks. As shown in the figure, when the first network is identified the image, we adopt a complementary correction network, CCN, to learn a residue based on the features of another network, such that the prediction of the first network can be corrected. And our model consists of two essential networks and a CCN, and the CCN is applied to learn the mapping from the raw output of the first network to the correct class label. CCN is able to outperform the first network and provide a training target of enabled data to the second network. We further perform the mutual learning between the two essential networks such that the complementary network can be ultimately transferred to the first network. And this is the architecture of our CCN. An important feature of CCN is the identity skip connection. In addition, the features from the second network are used as side input. The overall loss function of CCN is composed of a classification evaluation on labeled data and a consistency regularization on enabled data. And for the first essential network, the overall loss function is composed of three parts: the classification, evaluation, the adversary perturbation, and the mutual learning. To enhance mutual learning between the two essential networks, CCN provides the training targets of the enabled data for the second essential network. The second network can be expected to be complementary to the first one. And to highlight the effectiveness of CCN, let's have a look at the experimental result on the synthetic data. We visualize the learned decision boundary during training to illustrate how the CCN corrects the prediction of the first essential network. We can observe that CCN effectively converges to a better solution than the first essential network. We also verify the effectiveness of the CCN on CIFAR-10 with 1,000 labels. The left figure indicates that CNN and the second essential network has similar performances, and both outperform the first essential network without mutual learning. In the right figure, the amount of the true correction is much greater than that of the false correction, which indicates that our CCN does improve classification. And then we visualize what CCN learns, and given a set of difficult samples, the second column shows the raw outputs of the first essential network. We can observe that these images are misidentified. And the third column shows the residue learned by CCN. And when combining the raw output and the residues, this misclassification can be corrected. And on multiple benchmarks, the proposed model significantly improves the baseline model, and we also perform comparison with previous state-of-the-art methods. And then we compare the classification performance of the three networks in our model, and we can observe that they have a very similar performance. And to conclude, we incorporate the CCN into mutual learning model to capture complementary knowledge, and the CCN uses the features of one network to correct the output of the other network. Under the guidance of CCN, the network become increasingly complementary. And welcome to see us at poster 35, and thank you for your attention.
Hi, this is Yusuke Nitani from Preferred Networks. I'm going to present a training method for sparsely annotated object detection data set. With a fully annotated object detection data set, in principle, all objects of supported categories are annotated, as in Pascal VOC and MS COCO. This form of annotation requires large annotation cost, especially when the number of categories is large. With sparse annotation, annotation procedure is more efficient by only annotating subset of objects and images. This procedure is adapted by recently released Open Images dataset V4, which contains much more number of categories compared to previous ones. In Open Images dataset, categories with annotation depend on set of categories called verified categories, which are different among images. This means that for the same category, depending on images, there may or may not be annotation. For instance, Open Images dataset supports human parts categories, such as human arms. The image on the left contains annotation for these categories because these categories are included in the verified categories of the left image. However, the image on the right does not have annotation for them because these categories are unverified for this right image. There are two reasons why performance will drop due to sparse annotation. The first reason is fewer number of positive samples that can be used for training from each image. The second reason is increase in false negative samples during foreground assignment of proposals. This means that the network is falsely trained to predict proposals around objects without annotation as the background. For instance, in these images, proposals around the faces and arms are falsely assigned as the background during training. To solve false negatives problem, we propose part-aware sampling, which exploits parts relationship of certain pairs of categories. Parts and subject relationship of categories is interesting because this speaks a lot about spatial relationship of objects. For instance, bounding boxes of human parts, such as arms, appear inside the region of persons for most cases. Same goes for tires, which often appear inside cars. Based on this intuition, we ignore calculation of classification loss for our part category if a proposal is spatially inside the bounding box of subject category. For instance, with this image, given the ground truth person annotation, we ignore classification laws for human parts such as arms and faces for proposals inside the bounding box of person. Part-aware sampling relies on the assumption that a bounding box of part categories is spatially included in the bounding box of the corresponding subject category. We calculated the percentage of part bounding boxes that are included in subjects on open images data set for the pairs of categories we are interested in. From this calculation, we found that 93% of bounding boxes are included in the bounding box of the corresponding subject category. This number shows that our assumption relatively holds true for this data set. Here's the quantitative comparison of training with and without part-aware sampling. The bottom row shows the prediction by a model with our method. Clearly, with part-aware sampling, prediction of parts become more confident. Finally, this is the quantitative results on the validation split of open images data set. For human parts categories, we saw on average 22.7 average precision improvement from the baseline without part-aware sampling. For the 47 part categories that are relevant to part-aware sampling, we saw an average of 9.2 average precision improvement. We think that the improvement is significant, especially for those categories that often appear in the images without annotation. For instance, there's 45 average precision improvement for human ear. When we look at the images in the data set, we saw clear bias that annotation is often missing for this category. The trends hold true for other categories, which we saw quite a good improvement. And this concludes my presentation. Thank you.
Okay, are there any questions for these three talks? Okay. Oh. Keep hoping for a question. No? Okay. So for the second talk, I was wondering if you have any intuition whether your method relies on the uncertainty of or your mutual learning relies on the uncertainty, or whether the model is getting the prediction wrong. Like this mutual learning, do you know if whether it's relying on the entropy or the is there any way to figure that out? Have you thought about that? Is that an interesting question?
I think the key of the mutual learning is that we hope it's hard for two models to simultaneously make two they all make the warm decision. So the second one can be provide some target, some training target for the enabled data to improving the training of both the network. Thank you.
Yeah. Hello.
Oh, go ahead.
For Xinggang, for training, does this mean that the method only works where you have segmentation mask, where you know where the background is and where the object of interest is?
Yeah, so for this work, we don't have any segmentation mask, but at the background stage, we make that assumption that we have bounding box to know what the background patches are. But we have run recently a version where we assume the patches around the edges can be considered as background, so you can even get rid of the bounding boxes if you want.
Okay, thank you.
Okay, if there are no more questions, maybe we can move on to the next one.
Good afternoon. My name is Shi Yucheng, and I'm from Tianjin University, China. The title of our paper is Curse and Away, Boosting Black Box Adversarial Attacks. The GitHub page of our paper is below the site. I will introduce our work in three aspects. First is the definition of adversarial example and existing methods, then our curse and away attack, and finally, the experimental results. The definition of adversarial example is as follows. The dotted line in the figure indicates the decision boundary we want to separate blue cross and red circles, while the solid line represents the decision boundary that the model really learned. The attacker can add a small noise to the sample that is correctly classified so that it enters the area where two boundaries do not match and achieves misclassification. The formalization of adversarial attack is as follows. We want to sample X apostrophe that is classified by the human classifier F2 into the same category as the original image, but classified by machine learning classifier F1 into a different category. The distance between X and X apostrophe is less than epsilon. Existing attack methods can be divided into three categories: one-step gradient-based attacks, iterative attacks, and optimization-based attacks. Next, I'll talk about our curse and away method. Existing iterative attacks have diminishing marginal effect on iteration number T. The improvement of noise reduction gradually reduces as the iteration steps increases. We believe there are two reasons. On the one hand, existing iterative attacks and noises monotonically along the direction of gradient ascent, resulting in a lack of diversity and adaptability of trajectories. On the other hand, there are no refinement mechanism to squeeze redundant noises. This figure shows one possible distribution of target model loss function. Background is the contour of cross-entropy loss. The redder the color, the lower the loss. The consecutive black curve represents decision boundary between category snowbird and snail. In the case, the loss function rises slowly along the direction of gradient ascent, like the green trajectory. It may be possible to find a shortcut across the decision boundary from a nearby starting point, as shown by the purple polyline. So as for our curse iteration method, we first update the original image for one step along the direction of gradient descent. When the loss on the target model is still declining, continue to update along the direction of gradient descent, and vice versa. We abandon the monotonic search strategy based on gradient ascent to increase the diversity of iterative trajectories. On the basis of curse, we record and update the average direction of all adversarial examples of one image, and use as starting point when calculating gradients. We perform binary search between original image and adversarial examples to fully exploit the potential of this round. We also propose way optimization to squeeze out the redundant noises. We divide adversarial examples into groups and reduce noise magnitude group by group. After that, we set the value of each pixel to 0 with probability of sigma to perform more fine-grained squeeze. So the way optimization can also be used in targeted misclassification. First, we collect an image XT classified into the target category. Second, use binary search to find an image between the original image X and XT. After that, we use this image to guide the first gradient ascent step starting from X. Now look at the experimental part. All our experiments are performed on tiny ImageNet and ImageNet. The figure above shows the influence of iteration step T, binary search step BS, and the variance of Gaussian noise S to black box attack effect. The figure below demonstrates that whether it is curse iteration, binary search, or two steps in way optimization, each component can effectively reduce the noise magnitude. So for untargeted attack, we compare our method with three state-of-the-art iterative attacks: RFGSM, MIFGSM, and VRIGSM. Curse and way achieves smaller median noise magnitude in L2 norm than all other methods on different target models. Figure on the right shows several examples. In experiments on targeted attack, compared to three decision-based attacks, noise magnitude of our method is also significantly reduced. This confirms the effectiveness of integrating interpolation method into curse and way attack. Although defense and ensemble methods increase the difficulty of attack, the noise magnitude of adversarial examples built by curse and way is still much lower than other attacks. That's all for introduction to our curse and weight method. Our poster will be presented in 37th position. Thank you.
Hello, everyone. My name is Jared Sylvester from Booz Allen. I'm here to talk about barrage of random transforms for adversarially robust defense. There we go. Okay. Look at that. One slide in, I already missed my first cue. So by now you all are probably familiar with this image. It was in the last slide, for instance. And what this shows is that an adversary can fool the models that we create into making the incorrect output with high confidence by making only very small perturbations. These perturbations are very significant to the model, but they are imperceptible to you and I. And this is bad, obviously, right? So what are we going to do about it? Our idea is to beat the adversary to the punch and make some defensive perturbations of our own first. So what do I mean by this? I mean that at inference time, we would modify the input images before they're even fed into the network by doing something like blurring them or adding some noise or desaturating them, and that hopefully this would interfere with the adversary's ability to find a successful attack. Now, as some of you are no doubt aware, this has been tried before. It's a pretty good idea, and it didn't work, right? It only trivially interferes with the adversary. So if it doesn't work, why am I here, right? What makes our approach, what makes BART different? What we do differently is that we start with a very large arsenal of these potential transformations. We parameterize each one of them randomly, so we adjust the strength, the radius, the color channels it's applied to, and then we select a subset of these to actually apply randomly again, and then we randomly again shuffle the order of our subset, and we feed the input images through that subset in order, right, in a serial order. So you get this sort of pipeline that is different every time you go to do another inference. So as a result, you get very different effective input to the network each and every time, and it is very unpredictable based on the original input. So we see here in these 3 rows, 3 of the examples of the 25 overall transformations in our arsenal, and in each column, we have one particular random reification of that transformation. So you can see, for instance, in the first row where we alter things in the XYZ color space, things tend to come out quite differently each time. In the second row where we're operating in the lab color space, the differences are almost imperceptible, much like the attack perturbations. Now, when we do this, as I said, we have 25 of these in total. Each one of these on their own is extremely weak, right? They're effectively useless. Any one of these defenses, any one of these transformations can be defeated by an adversary 100% of the time. However, when we ensemble them together with their powers combined, they become extremely strong. And this is because you're not really getting to attack the kind of cute puppy on the left. You have to attack the kind of nightmare terrier on the right, or more appropriately, the expectation over all of those frames you're seeing. And there isn't that much information in that expectation. Every time the adversary goes to take another gradient step to attack you, we haven't really moved the goalposts on them, we've moved the starting position. And as a result, there's not a consistent direction for the adversary to move in to figure out how to cross that decision boundary. So before I discuss the results, I want to say that we tried as hard as we could to form a very strong adversary to test this defense on. We based most of it on PGD attack. We implemented BPDA and expectation over transform to allow the adversary to backprop through all these transformations we applied. We were completely white box. We allowed the attacker to know the parameters of our defense in addition to the network itself. We allowed huge adversarial distances, and we even went so far as to create a new attack we thought might work a little better. So does this work? I think so. I'm very happy to say that we were able to get a top 1 accuracy above the top 5 accuracy of the previous best defense that we found, which was adversarial training. We can also do things like vary the number of transforms that we select. So this shows us going from no transforms, which is no defense at all the way up to 10. And as you do that, your accuracy when you aren't under attack does start to drop off, but you add in resistance to adversarial attack. And we can do this in the targeted attack scenario as well. When you crank that number of transformations all the way up to 10, we can reduce the attacker success rate down to 0. So, in conclusion, we have combined some domain knowledge in the form of these visual transformations with lots and lots of randomness, and by ensembling these together, we're able to develop a new defense against attacks. We think this is pretty useful in the short term because it's very easy to implement. We hope this also gives the whole community some ideas for potential ways to do long-term defense in this kind of ongoing cat and mouse game by showing that even completely useless, weak defenses, when combined together appropriately, are quite useful. So on behalf of my co-authors, Edward Raff, Stephen Forsyth, Mark McLean, thank you for your attention, and we hope to see you at poster number 38 this afternoon.
So good afternoon, I'm Zhaojin from South China University of Technology. Today, I would like to present you aggregation cross-entropy for sequence recognition. The presentation concludes three parts: introduction, aids, and experiment. So first part, introduction. Traditional method for sequence recognition problem can easily result in inconvenient pre-segmentation and post-processing stage. The recent emergence of CTC and attention elegantly solved the problem. However, they still have their own drawbacks. For example, CTC can hardly be applied to 2D prediction problem. Attention uses too much memory and training time. So we go to second part, ACE. Therefore, we proposed an aggregation cross-entropy loss function with only three simple stages. First, aggregation of the probability for each category around the time dimension. Second, normalization of the accumulated result and label annotation as probability distribution over all the classes. Third, comparison between these two probability distribution using cross-entropy. Okay, so how do we derive the proposed ACE loss function? First, we have the general loss function for sequence recognition, where I represent the input image and S is the test annotation. Rather than directly calculating the probability of S given I or the probability of S subscript L given L and I, we choose to supervise only the accumulated probability of each classes. So how do we, so how do we supervise the accumulated probability? A most simple and easy way is from the perspective of regression. However, regression method will result in gradient vanishing problem, which is caused by the tiny prediction of the network. To solve this problem, we use cross-entropy to measure the distance between two probability distributions. First, we normalize the accumulated probability and its annotation, then require them to have the similar distribution. And the gradient vanishing problem is solved because the tiny prediction of the network is elegantly offset by themselves. And the proposed ACE loss function can also be used for 2D prediction problem. All you need to do is directly flatten the 2D prediction into 1D prediction. The basic operation in ACE can all be implemented in parallel with GPU. So the inference and backpropagation are much faster than that of CTC and attention. The proposed ACE loss function requires nearly no memory consumption because ACE loss result can be directly calculated based on the four fundamental formulas. So we can draw a conclusion. ACE has no parameter at all. Its memory consumption and runtime is significantly less than that of CTC and attention. So final part is experiment. First, we have the skin test recognition task. In this figure, it can be observed that the cross-entropy-based ACE attain a much better result. This way. And in this figure, we can observe that the higher shuffling ratio of the characters in the test annotation, the worse the performance of CTC and attention, while ACE remain the same accuracy result. In this figure, the slope current shows the 2D prediction of the recognition model, which has very similar character distribution with the character in the original image. We also investigate the task of counting objects. In this figure, the counting model assigns different level of attention to different parts of an object. For example, the cutting model pay more attention to the face or a person. This phenomenon corresponding to our intuition, because face is the most distinct part of individual. So now this is the conclusion. Thank you for your attention. Welcome to visit our poster.
Okay, we have a few minutes for questions. So I have a question for the second. Oh, go ahead, go ahead.
I have a question for the second one too. So you see the attackers, they are in the driver's seat. So the best that we can do so far is, well, when you have an attacker, you understand, you build your defense, right? Mm-hmm. So isn't this a winning, is that even possible in the future that you can develop such a technique that is immune to any attack based on your research? Give us some thought on this. Is this a winnable war at all?
No, I don't like to think about this as a question that is either going to be won or lost. I kind of think about this from a security standpoint. Cryptography can be beaten. It's a question of how hard you have to make the other guy work. And so I think the goal that we should be shooting for realistically is not to absolutely preclude the ability of an attack to work, but just to make the attacker, make them sweat, make them work for it, make them put in effort.
Any other questions? I guess I'll ask mine. So also, do you think is your method kind of domain dependent? If I try this on medical images, would it be different? I know this is probably too much to ask, but.
I'd hesitate to speculate. We certainly haven't tried that, and I've never worked with medical images before. It seems like it would work. There's nothing, if you chose the right set of transforms, that I think would preclude it from working again. I think there's a big open question as to how we might expand this into other domains. What other of these kinds of semantically meaningless but kind of numerically relevant transformations could you apply? We can think of some for sounds, but what would you do with 3D point clouds or anything else? I'm really not sure, to say nothing of other types of images, but I'd love to find out.
Okay. If there are no more questions, let's thank the speakers again.
Time to wake up. Hi, my name is Amit from IBM, and I will be presenting Lasso, a neural network which does a feature manipulation using set operations, and it's used for few-shot classification. Imagine I want to train a classifier for animals, but I have no data. So I go to the zoo, I take a few pictures of animals, and train a CNN. But in all my pictures, the animals are in cages. So when I try and classify animals in the wild, it doesn't work so well. Now in some feature space, imagine if I could isolate those cages features and then remove them from my training examples. By that, getting training examples of animals in the wild. Or instead of all that hard work, just go to the safari instead of the zoo, right? Okay, so the inputs to our network are two multi-label images. X has person, dog, sheep, Y has person, dog, cat. The images are projected to a feature space using a CNN feature extractor backbone. And then the feature vectors are fed into the free set operations networks. The goal of each specific set operation network is to synthesize a new feature vector given two input feature vectors, so that the semantic content of the synthesized fake feature vector will correspond to a set operation on the input vector's labels. So for example, for union, we will be receiving a feature vector with all the labels from both two input images, person, dog, sheep, and cat. Let's denote those set operation networks in red as the lasso networks. As we just saw, we have our real feature vectors, fx and fy. We have the intersection, union, and subtraction set operations networks in red, and their outputs, the fake feature vectors z. The classification loss we use to train the lasso networks is calculated by taking those fake feature vectors z, feeding them to a pre-trained classifier, and calculating a binary cross entropy, or BCE loss, between the classification scores and the expected labels for each specific set operation. So again, for example, for union, we will be comparing the classification scores to a binary vector with all the labels from both two input images. Similar to adversarial loss, the lasso networks tries to fool the pre-trained classifier. The second kind of loss we have is the reconstruction loss. The first variation of it using MSE is the symmetry loss. It ensures that the outputs of the union and intersection networks will remain the same even if the order of their inputs is flipped. The mod collapse loss helps in increasing the diversity of the fake outputs by creating a cycle loss between fx and its synthesized reconstruction with the fake lasso vectors. We have been testing the quality of those vectors for a few different ways, both for classes which were and weren't seen during training. Looking at classification, MAP, the pre-trained classifier accuracy for real image vectors is around 75%. The fake lasso vectors managed to achieve similar performance. We also did image retrieval in the feature space, and also here, the fake lasso vectors managed to achieve similar performance to the real vectors, both for classes which were and weren't seen during training. We used image retrieval in order to get a visualization of those fake feature vectors. So on the left, you can see an example of two inputs, a cat and a toilet. The results of our lasso union network is a cat in a toilet. And of course, we have some results for subtraction and intersection, and unfortunately, some failures. Few-shot learning is an interesting task of learning from very limited training data of very few, maybe even just one example per category. Building on Lasso's ability to work on classes unseen during training, we approach a new task in few-shot learning. Learning from very few training images, each image contained a few different objects instead of one object per image. We propose the first benchmark to the multi-label few-shot classification task. We used Lasso to do data augmentation by synthesizing fake feature vectors for training and show a noticeable improvement across a range of baselines. For more information, insights, questions, come to our poster number 40, or to the IBM booth. Thank you.
Hello, I'm Davis Wertheimer, and today I'll be presenting my work with Bharath Hariharan on few-shot learning with localization in realistic settings. I'll start by highlighting two broad trends in image recognition benchmarks. First, we have what I'm going to call traditional recognition. Traditional recognition includes datasets like CFAR 100 and ImageNet, which feature a large number of categories and large quantities of training data within each category. For our purposes, large is on the order of hundreds. On the other end of the spectrum, we have few-shot recognition benchmarks, such as OmniGlot and Mini-ImageNet. The evaluation tasks for these benchmarks feature very small numbers of categories with very few training images available per category. Here, very small and very few typically mean 5. The problem with this setup is that the real world usually doesn't fit nicely into either of these settings. Images in the real world often follow a long-tailed distribution, where some things are very common and most are relatively rare. This is important because it is not clear that models which perform well on either traditional or few-shot benchmarks can generalize to long-tailed settings. In support of my claim that the real world is often long-tailed, I offer this sampling of image recognition datasets. In each of these, the largest category outnumbers the smallest one by at least a factor of 10. The last two entries are particularly notable in that they were explicitly designed to reduce this disparity, but even so, still display the same order of magnitude separation. We therefore design a practical, long-tailed, few-shot recognition benchmark. We sample images from iNaturalist, a collection of photos of living things taken in the wild by citizen scientists. The resulting meta-INAT benchmark features a large number of classes of varying sizes. The images are of realistic quality, and bounding box annotations are available as a valuable source of side information. We evaluate a number of baselines and see that our initial intuition is correct. Neither traditional nor few-shot approaches work well on meta-INAT out of the box. Training a softmax classifier directly on the evaluation task leads to a large disparity between the overall and per-class accuracy. That tells us that the network is ignoring small classes in favor of large ones. Standard techniques for preventing this, including weighted loss functions and proportional data sampling, only hurt performance. Transfer learning, with training and then fine-tuning, performs comparably to prototypical networks, a recent few-shot approach which we use as our baseline. Both numbers, however, are below what we'd like to see. We now introduce 3 simple, parameter-free techniques, which, taken together, allow us to double the accuracy of prototypical networks on meta-INAT. Due to time constraints, I'll give only a very brief overview of these techniques. Details can be found at our poster session, and I'd be happy to talk offline. First, we note that prototypical networks are trained using simulated few-shot learning tasks, where the size of the training set in each simulation impacts learning heavily. To mitigate this, we introduce batch folding, which simulates leave one out cross-validation instead, allowing us to get cleaner gradients than the traditional train test partition. Second, we observe that a tiny amount of extra information, like a few bounding boxes, is often relatively easy to acquire. In few-shot localization, we leverage as few as 1 bounding box per category to isolate the region of interest in each image before classifying it. Third, we show benefits from using channel covariance to rapidly expand the feature space without blowing up the parameter count and overfitting to the training data. Each of these techniques independently contributes to a sizable jump in performance. They are also mutually beneficial and altogether double the mean accuracy of prototypical networks on meta-INAT. While this jump in performance is significant, our baseline comes from an admittedly low-capacity model, a network with only 4 layers and no skip connections. To see if our techniques generalize to more powerful models, we replace the first 2 prototypical network layers with a pre-trained ResNet 50. While the overall gain from our techniques does shrink slightly for these models, they still collectively contribute a comparable 13-point improvement. Thus, batch folding, few-shot localization, and covariance pooling do generalize to more powerful models. They also generalize to settings with substantial domain shift and, to a limited degree, the original mini ImageNet benchmark. To recap, we introduced meta-INAT, a new, long-tailed, few-shot recognition benchmark built toward practicality and realism. We showed that traditional approaches do not work well out of the box on this benchmark, and introduced 3 parameter-free techniques which double the accuracy of baseline prototypical networks. Our techniques have generalized to a wide range of other settings, and our code is available online. For the full set of results, as well as details on our techniques and their implementations, please come visit us at poster number 41. Thank you.
Hi everyone, my name is Mancini Massimiliano from Sapienza University of Rome, and today I will present the graph, Unifying Predictive and Continuous Domain Adaptation through Graph, a work by me, Samuel Rotabulò, Barbara Caputo, and Elisa Ricci. The goal of standard domain adaptation is to produce a model for a target domain, given labeled data in a different source domain. Usually, the 2 domains have different distributions, so the presence of target data is fundamental to characterize the shift existing among them. Here, we ask ourselves whether we can still address the A, even when we have no data for the target domain, but different kind of information. In particular, is adaptation possible if you adjust a description of the target domain? This setting is known as predictive domain adaptation. We have a labeled source domain and a set of unlabeled auxiliary domains. For each of them, a description is attached in form of metadata. At test time, we receive the metadata relative to the target domain, and we use this metadata to estimate the parameters of a model for the target. Notice that this is possible only if, during training, we understand the relationship existing among domain metadata and parameters using the source and auxiliary domains. Obviously, if you have no supervision, our metadata can be noisy. So we devised also a way to recover the working parameters, let's say, if our initial estimation is bad. To do this, we exploit the stream of target data we receive at test time to refine and continuously adapt our model. So let's suppose we have our set of source and auxiliary domains. What we can do is to instantiate one node per domain and learn domain-specific parameters. Obviously, for the source, we can use standard supervised loss, while for the auxiliaries, we can use domain adaptation techniques. Obviously, since these nodes have also metadata associated, we can connect the various domains and build a graph. In the graph, each node is a domain and has attached parameters, while each edge denotes the relatedness among the metadata of the different domains, with the relatedness just denoted as distances among metadata. At this time, we receive the metadata relative to the target, and we instantiate a node, connecting it to the others. Obviously, this node has not any data associated during training, so we have no parameters as well. If we assume that closed node in the graph requires similar domain-specific parameters, what we can do is just to propagate them. And what we do is to obtain the target model by propagating the parameters relative to nearby nodes in the graph. The way we propagate this node is just a weighted combination with the weight proportional to the strength of the edge connecting a node to the target one. Here we sketch how we apply our graph within a network. We replace the standard batch normalization with our graph-based batch normalization layers. Since we stick to BN-based domain adaptation, we have that for each domain, we have the specific domain statistics and the scale and the bias. For details on this procedure, since we use also the graph, please come to our posters. Now, the last thing is if we can recover the parameters in case of a bad estimation. And the answer is yes, if we use the stream of incoming target data. Obviously, for the statistic, what we can do is just to update them as the data come. While for the scale and the bias or other domain-specific parameters, we must define an unsupervised objective and just optimize for that. In this case, so we can get a better estimate and eventually recover from the initial mistake. Here we show the results of our approach on the century of portraits dataset, where the task is gender classification and the metadata are the year and the region of the picture. Our model outperforms the source-only baseline, and with the refinement strategy, we are able to almost completely fill the gap with upper bound, a batch norm-based DA model with target data available. We also perform experiments on the Concars dataset, comparing our model with the previous state-of-the-art of Yang and Hospedales. Here the task is car type classification, and the metadata are the year of production and the viewpoint. Our model outperforms both the baseline, and with the refinement, we fill the gap with the upper bound again. Thank you, and if you have any questions, please come to our poster number 42.
Last chance for questions for these three talks. I have to have a question, right? So I have a question for the third talk. So how easy is it to construct this graph? Like especially if your metadata is noisy, if it's not a clean label like rear view.
Okay, well, at the moment, for the experiments, we assume that the metadata are quite clean. I see that it's time for the coffee break. So the metadata are pretty clean, but we may refine. They may not capture the exact relationship among the domains. So we receive a metadata that maybe is not helpful for covering the domain shift, and then the continuous refinement strategy allows us to obtain a better estimation for our model. Actually, we plan to, now the edges are fixed, and we plan to learn them and refine them, taking into account how related they are, the metadata.
Oh, we have a real question. Awesome.
Yeah, real question. For the second paper, you said that weighting losses didn't help. Did you try the focal loss that was originally designed for recognition, but also was meant to solve the the heavy-tailed distribution of classes problem?
No, we didn't. I admit that we only tried that one loss, mostly because even if we did manage to get the perfect reweighting case where you get the per class accuracy up to the total accuracy, it's still underperforming compared to baseline prototypical networks and baseline transfer learning.
Cool. Thank you.
Any others? Okay, so that concludes our session. Thanks for sticking around till the end. Let's thank the speakers.